right. So we left off on Friday talking about Avogadro's number, and we also talked about moles, um, how the moles actually connected both the macro and micro realms, and um, we also talked about the definition of a mole being the amount of a substance that contains the same number of atoms or molecules or ions as a pure sample of a carbon-12 isotope with a mass of 12 grams. So we talked about that being the definition of mole, and then how moles actually link bulk mass, and which is macro, and then the micro realm, which is the number of atoms or molecules or ions that we call discrete particles. All right, and then we talked about how Avogadro's number is used to determine how many discrete particles are in a mole, right? So we use that Avogadro's number. We're going to use this today as well to kind of discuss uh, the particles per mole, the atoms per mole, ions per mole, molecules per mole, and so on and so forth. And that number is a given number 6.022 times 10 to the 23rd particles per mole. And that's, again, interchangeable. So today we're going to push this concept a little bit further, and we're going to talk about molar mass, and how molar mass is basically the way that you connect bulk mass and moles. So let me just start a new page here. And today is the 24th. Can you believe that? We've got 4 days left in this month. It's crazy. All right, so we're going to begin talking about molar mass, right? And this is a continuation of the previous section that we've already been discussing. All right, so we've talked about moles. We've talked about the connection that moles and bulk mass have. These two things being connected together uh, based on a couple of things. Number one, the relationship between atomic mass units and grams per mole. And we also talked about the relationship between the 12 grams of a carbon-12 isotope and how that relates to moles. So that's, you see the connection between mass and moles already, but we're gonna push that a little bit further and talk about what we call molar mass, because we even calculated formula weight or molecular weight, but we did it in terms of AMU, right? So now we're going to talk about molar mass, which is represented by this unit, grams per mole, right? So it's grams per 1 mole of a substance. All right. And again, we can express this as AMU or grams per mole. All right. We've been working with AMU previously, but now we're going to work also in grams per mole. And the reason you can do that again is because the carbon-12 isotope, the definition of a mole is the 12 grams of a carbon-12 isotope, and the amount of a substance that contains the same number of atoms or molecules or whatever as in a pure sample of carbon-12 with a mass of 12 grams. So that allows us to go between these two units. And so when we're able to do this, now we can develop or derive some new relationships based on the relationship between AMU and molar mass, right? So normally, and this is the way that I learned this as an undergrad. I had a fantastic chemistry teacher, or G-Chem teacher as an undergrad, and he just put this simple equation on the board one day. And that equation allowed us to derive any one of these entities right? If we had the other two. So molar mass, MM is molar mass. Let me give you that now because I'm gonna abbreviate it for the rest of the time. Is grams per mole, right? If you have any two of these values and you need the third one, you can simply manipulate this equation, right? So molar mass times moles is grams, right? By the same token, grams over molar mass is moles. Now that might seem very simplified, but I promise you, this is indispensable to you as a chemistry student. When you get to when we get to the point where we're doing limited reagents, when we get to the point where we're calculating theoretical yields, where we're calculating the amount of moles in a particular solvent, I'm sorry, solute, when we get to molarity, this manipulation of this one simple equation is critical. So if you're able to manipulate this, that's going to help you going forward. All right. So we're just going to do some molar mass examples. And I'm going to switch pens. And we're going to do a bunch of examples with molar mass. And the reason is because, again, practice makes perfect. The more reps we get, the better we become at what we're doing. All right. So right. And then in these examples, you're going to see multiple ways to apply this information. You're going to see ways to just go straight from grams to moles. You're going to see ways where we might start with uh, a mass percentage of something and work our way back to moles. Like there's, and the reason we're doing it this way is because I never like to box students in. I don't want you boxed in thinking, oh, I'm only going to see this one way, right? You can see this on the exam, this particular concept in multiple manifestations, a lot of different ways you can see it. All right, so let's look at this first example. And we're just going to call this example A. And we got 4.7 grams of potassium. And I'm not writing out the question, I'm just giving the information. And we want to know how many moles of potassium. All right. What we need, again, here's our equation: grams over moles equals molar mass. Right. So if we want to know how many moles, we just need to manipulate this. We can say grams over molar mass equals moles. And I'll be honest with you, as a chemist, once you learn, even though you're not a chemist, but you're taking chemistry, I'm just saying as in general, once you learn how to manipulate relationships between different entities, different units, it changes the whole game because there's literally nothing you can't solve for. You can solve for anything. If you know the relationship between the pieces or the components, you can literally solve for any variable or anything that you're looking for, right? And even there's even the idea that if there's another way to get at one of the variables and we have the data for that way, but we don't have the variable, we can substitute that in for that variable. So that you're going to see this a lot. And I'm just trying to prep you and get your mind thinking, outside the box. All right. So what do we need in order to solve for moles? We need what? The mass. And we need what? What else? The molar mass. Right? Do we have the mass in the problem? It says the problem gave us 4.7 grams. So we have the mass. And all what we need now is the molar mass. So the mass is 4.7 grams. The molar mass we take simply from the periodic table. So the atomic mass of the element we can use as the molar mass, because again, that's listed in AMUs, but we can take the AMU and turn it into grams per mole without a conversion. All right. So the atomic mass for potassium is 39.10 grams per mole. All right. So all we're doing now is taking those two numbers and dividing them. Grams over molar mass is 4.7 grams divided by 39.01 grams per mole. So the grams are going to cancel, moles will come to the top, and then that will give us 0.12 moles of potassium. Any questions about that? So again, if you have the element and you don't have a molar mass, it's understood that you can just pull the atomic mass from the periodic table and use that. Right? Those numbers are very important. All right. Any questions so far? All right. Let's do another example. Let me get this out of the way. We won't need this yet. Right. So here, I'm going to ask another question at the end of this question too, because I just want to see if you remember from the first chapter, something that we covered. So we're gonna take 1 liter of argon gas. Sorry about that. And that 1 liter of argon gas is composed of 9.2 times 10 to the minus 4 moles. All right. The question is, how many grams is this? And how do we determine how many grams if we have moles? What else do we need? All right, so grams is what? Moles times, I'll just put an X, not a dot, times what? Molar mass, is that right? All right. So we know the number of moles, we know the molar mass. It says argon, it's giving us argon. All right. So we know, if we know argon, we can get the molar mass from the periodic table. So that is, argon has a atomic mass of 39.95 grams per mole. Highlight that. 39.95 grams per mole. So all we're doing here, if we want to solve for grams, is put in 0.00092. And this is in moles. Yeah. And then we're going to multiply that by the molar mass of 39.95 grams per mole. So moles are going to cancel and we're left with grams. Can somebody do that calculation real quick? Tell me what you get.
I got 0.036775.
So let's just go ahead and round it up to 37. 0.037 grams. Good. All right. Let me ask this question. I will buy you lunch if you can tell me what the density of argon is based on this equation. How do we calculate density? Tell me the density equation. And I'm just throwing this in because I like to like show relationships between things. Anybody?
Is it mass over volume?
Come on with it. Mass over volume. Do we have a mass that we just calculated?
Yes, sir.
And it is, in this case, 0.037 grams. And we have a volume, don't we? So we need to, all we need to do is take that volume and make it into milliliters because it's in liters right now. Because density, the units are grams per milliliter. So we need this in milliliters. That's in grams, right? So 1 liter is 0.001 milliliter. No, sorry. It's 1,000 milliliters, my bad. All right. What do we have? What's the density of argon gas based on these numbers?
Is it 3.7 times 10 to the I don't know. I think it's 10 to the 6.
-6.
Yeah.
All right, good. I just threw that in because again, it's a way to show the relationships between the numbers that we're working with. Because it gave us a volume, but imagine a problem where you didn't have where you had a volume and a density, but no mass, but it asked you to find a number of moles. You can always manipulate the density problem to get the mass. And then based on that, you're able to find out, once you get the mass, you can figure out the number of moles using the molar mass. I just wanted to throw that in there. Keep you on your toes. All right, let's do another example. Because I mean, we're gonna kind of beat the dead horse here just for a minute. Because this is a manipulation that you're gonna use multiple times. You're gonna use this over and over again throughout the class. So let's do another example where we have 5 grams of copper wire, and we want to know how many atoms are in that 5 grams. So 5 grams of copper wire. Right. How many atoms are present? All right. And so when we have that, how do we go from, is there a direct route from grams to atoms? Can we just do a direct calculation and go from grams to atoms? All right, there's no direct route, no direct calculation to go from grams to atoms, but we can go from grams to moles and then from moles to atoms. Again, it's another one of those type of problems where you have to think about the calculations and what you have versus what you're looking for. All right. So we can go from grams to moles and then moles to atoms. How do we go from grams to moles? What do we need in order to carry that out? Anybody? Don't we need the molar mass? And in grams over molar mass, wouldn't that give you moles? Based on what we just did up here, right? grams over molar mass is right here. Equals moles, all right? So we can convert from grams to moles using molar mass. How do we go from moles to atoms or moles? An atom is one of those discrete particles, right? Like an ion or a molecule. So how do we go from moles to discrete particles? We need Avogadro's number. And I'll show you, but I'm just trying to make sure we're good. So now, again, grams to moles, we need grams over molar mass to get moles. Right, we have grams. We got 5 grams of copper wire. What's the atomic mass of copper? Based on the periodic table. Isn't it 63.55 AMU? Right, but we'll use grams per mole because again, you can interchange grams per mole and atomic mass units. Somebody do that calculation for me. 5 grams divided by 63.55 grams per mole. Anybody got it? I can't see the chat, so if you put it in the chat, just go ahead and unmute. Is that what you have? Those of you who calculated it, 0.079 moles. All right. Now, how are we going to go from moles to atoms? What do we need? How do we set that up? If Avogadro's number, so this is grams to moles, to go from moles to atoms, we need Avogadro's number 6.022 times 10 to the 23rd atoms per mole. Again, this is very important. That number here is always in moles. It's the discrete particles per mole, atoms, ions, molecules, whatever. So to be that times 0.079 moles. What do we have? Somebody calculate that real quick. I can't do it. I need to find my like real calculator. I can't do that on my phone with the Avogadro's number. All right, anybody got it? Don't all jump on the mic at once. Now we might crash the internet if we do that.
Is it 6? 6.022.
Yes, 6.02. Are you saying that's what the answer is? Or is that what the number is right here?
Yeah, I multiplied it right. That's what
So
I'm
that
saying.
times 0.079. I think the answer we got this morning was 4.74 times 10 to the 22nd. Right. So what that literally means is that in a five grams of copper wire that you can go buy at Lowe's, there are 4.74 times 10 to the 22nd copper atoms in that spool of wire. That weighs 5 grams, or a piece of wire that weighs 5 grams, because the spool is much heavier than that. All right. So again, this is a way you can see this. We start out with a mass, and we want to find out how many atoms, but there's no direct way to do that. But we could go from moles, grams to moles, and then moles to atoms and do it that way. So that's one way you'll see these types of problems. Again, I'm just trying to show you multiple ways of doing it so that when you see it on the exam, like you're not blindsided by it. Right? You're not getting caught off guard by it. All right. Let's do another example. Let's take we did this one this morning, and we have so what we're going to do in this example is we're going to derive the number of atoms using mass. Right. So this is a multi-step problem. Right. Again, there's no direct way to go from mass to atoms. And so we have to, this problem involves multiple steps. So we're going to go through this step by step, piece by piece. We're just going to walk it down. Right. So we have a 40 milligram sample of saccharin. Anybody know what saccharin is? The common use for saccharin. This is the structure. This is the main component in sweet and low, but it's also a carcinogen, which is kind of why I think it got to be a hydrogen here. Kind of why I don't think I put the hydrogen on this morning, but that's kind of why people have started using stevia and other sweeteners like that, because saccharin is a carcinogen. Sweet and low equal. I hate all of it. It tastes like crap to me. But this is what the principal component is in those artificial sweeteners. So this is saccharin. It has a molecular formula of C7H5NO3S. So this is the molecular formula. All right. And we got a 40 milligram sample. And one of the questions is, for this particular example, the question is, how many molecules of saccharin are in that 40 milligram sample? So let me write that out. I'm going to abbreviate this. And again, this is a great example of how you can connect the macro to the micro. All right. What's your strategy here for a problem like this? What all do we need in order to find out the number of molecules? There's no direct way to go from grams to molecules either. But we can go from what? We can always go from grams to moles, and then moles to molecules. That's important to understand that sometimes you have to take an indirect path to get the information that you need. So grams to moles, and then moles to molecules. How are we going to go from grams to moles? What do we need? Help me out. We got 9 minutes left. Some of you wish it was 1 minute, but we got 9 minutes left. What do we need to go from grams to moles? We need the molar mass. Grams over molar mass equals moles. And then to go from moles to molecules, we're going to need Avogadro's number. How do we get the molar mass if we don't have it? If we have the formula but we don't have the molar mass, how do we get the molar mass? What can we do to find it? This is the first thing we started this chapter out with, calculating formula weight, which we later call molar mass or molecular weight. How do we do that? We got 7 carbons, is that right? So 7 times the atomic mass of carbon, and then 5 times the atomic mass of hydrogen, and then 1 times the atomic mass of nitrogen, and 3 times the atomic mass of oxygen, and then 1 times the atomic mass of sulfur. Right? Those numbers, those subscripts matter. There's 7 carbons, 5 hydrogens, 3 oxygens, 1 nitrogen, and 1 sulfur. So when we calculate that, I'm not going to have you do that now. I'm just going to put it here. The molecular weight of saccharin is 183.1 grams per mole. So now we have another piece of data. We can do some work, because if we have the molecular weight and we have the mass, we can find the number of moles. So it's going to be grams over molar mass equals moles, right? We have one other thing that we have to do, because our mass is given in milligrams, but we need it to be in grams, right? So we got to calculate, we have to do a unit conversion here. Sorry about that. To go from, take that prefix off and go from milligrams to grams. We know that 1,000 milligrams is 1 gram. So we just take that number and divide it by 1,000, right? So it'll be 40 times 1 gram over 1,000 milligrams, right? So that's going to end up being 0.040 grams. So now we have a mass, right? We got 0.04 grams. We got a molar mass. And now we can just plug those numbers in. So that's going to be 0.04 grams divided by what? Uh-oh. That's terrible. Never mind. All right. It's going to be divided by that number we just calculated, which is 183.18. Grams per mole. Somebody do that calculation real quick.
Is it 0.00021?
Is it 2, 1? What's after the 1? Can we round up?
Yeah, you can do 2 too.
Okay. All right. right, cool. So this is in moles. Good, thank you. All right, and then now this is we did all of this to get to the position where we have moles and we can convert that into molecules of saccharin, right? So this number, we're just gonna plug in. Actually, I'm just gonna do it right here. I'm just gonna take this and multiply it by Avogadro's number. So this, I'm just gonna put this here times, somebody go ahead and be working on that, 6.022 times 10 to the 23rd molecules per mole. Let me shrink that a little bit so I can squeeze that in. This is molecules per mole. All right, so moles will cancel, and then we're left with molecules. Right, anybody got that calculation yet?
Is it 1.324?
I think this morning we had that number is close. We had this morning we had 1.315. What's your exponent? Times 10 to the what?
To the 20th?
20. Good. So you in the ballpark. I think, did you keep the number that you had, 0.0021 such and such and such? Or did you round it?
Yeah.
Yeah.
Yeah, I did.
Okay, yeah, that's why it's a little bit off, but that's fine. Thank you for the calculation. So this is molecules. All right. So that's how we can go from mass to molecules. We need the molecular weight and we need Avogadro's number. Oh boy, it looks like some second grade writing. Sorry about that. All right. So now there's one other part to this question, and then we're actually going to stop with that. And then on Friday, we're going to start talking about percent composition, because I don't want to try to jam that in a minute. But there's one other part. What if we asked how many carbon atoms were in that sample? How can we answer that? What information do we already have that we can use to answer that? Right, we got the number of molecules. All right, if we look at the molecular formula, how many carbon atoms are in one molecule of saccharin?
Is it 7?
Seven carbon atoms in one molecule. So if we want to know how many carbon atoms are in the whole sample, we can just take that number, 7 carbons per one molecule, and multiply it by this number right here, right? Because that's how many molecules are there, 1.315 times 10 to the 20 molecules. Right, so the molecules will cancel, and then from here, you can calculate that. You don't have to do it right now, but you can calculate that, and this will give us the total number of atoms. And as you can imagine, you can do the same thing for any of the other atoms: nitrogen, oxygen, sulfur, right? You can convert that into, you can find the number of atoms in the molecule for any one of them. All right, so with that, I don't want to start percent composition yet, but I just I want to give you like I guess the introduction. So that's that whole section with percent composition is going to be the section on based on determining empirical formula. So that's what we're going to pick up on Friday, determining empirical formulas. All right, we're going to start there on Friday, talking about percent composition and empirical and molecular formulas. All right, so we stop here. Any questions before we sign out? All right, if not, then we'll just pick up on Friday. Hopefully you enjoyed your mental health day yesterday. I don't know if I actually had one because my phone kept
Actually, I have a
going
question.
up. Go ahead.
Our first in-person lab is next Wednesday, right?
Yeah, because
Okay.
yesterday we didn't have class, and if you're in that Wednesday lab, it was scheduled for yesterday, but so keep that announcement because all the information is going to stay the same.
Okay, thank
Yeah,
you.
nothing is going, I'm not going to send out a new announcement. I may repeat that one on Tuesday afternoon, but yeah, everything's going to be the same Zoom link, same everything.
Thank you.
I'm trying to think, Alexis. I'm not sure. Can you just type in the chat what you were asking? Because I don't know. I haven't checked my email yet.